Okay, so I'm just reviewing here what we've covered last time on the properties of the SYK model. So it's a model of interacting fermions, C, which are on n sides with a random two-body interaction. So the n to the fourth random matrix elements, but this acts on a Hilbert space of size 2 to the n. Then you have a chemical potential, which you can choose, and we are interested in following the ground state and excitation of the system as you change mu, and that will determine the value of Q. So you can just, all right. So in the large n limit, the solution of this Hamiltonian reduces basically to solving these two equations. You have Dyson's equations as usual, but with no bare dispersion, just the self energy and a chemical potential. And the self energy is basically the cube of the Green's function. All right, so at this point, here are the two equations, you have to solve them, okay? There's of course some other constraints that I haven't mentioned, which is come from the positivity of the spectral weight, which follow from the spectral representation of Green's functions and the analytic properties in the frequency plane. So those are important constraints on the type of solution that are allowed. But you do find solutions that satisfy all of those constraints. And the general solution has the property that at zero temperature, T equals 0, if you look at the imaginary part of the Green's function, this is what you measure in a photo emission experiment, then you get a very large enhancement of the density of this Green's function at zero frequency, right, at zero energy. It diverges as 1 over square root of omega, both for adding particles, which is positive frequency, or removing particles, which is negative frequency. And the square root of omega is intimately connected with the fact that you have 4 fermions here. If you took other models with 6 fermions, you get different powers, but the structure is basically the same. So for now, in the first part of this lecture, I'm going to focus on these coefficients here, C plus and C minus. So both can be determined completely from staring at these equations and solving them, and the solution is the notes. But the important thing for our discussion here is the ratio of these two. And the ratio is a dimensionless number, and we just parameterize by this number E. Okay. All right. Now there turns out to be a very nice connection between this number E and the charge Q. So there's a solution for every mu, which changes the charge Q, and that ends up changing what you can think of as the particle-hole asymmetry. I mean, in some sense, so in a Fermi liquid, that's also what the Fermi wave vector is, because the Fermi wave vector is the point where the particle-hole asymmetry changes. Below inside the Fermi surface, you can remove particles easily. Outside the Fermi surface, you can add particles easily. So there's a location of KF. Here, there's no KF, but the change from particle-like to hole-like is characterized by the ratio of these two numbers. So this at zero energy, and this number turns out to be related to Q. So the notes have some discussion of how this is obtained, and it's a known relation. You can write it down in terms of a few simple tangent and sine functions and things like that. But I won't derive it because there's many other things I want to say. Really, I could go, there's so much work been done on this and other models that there's a lot to say. I just want to pick and choose a few things and move on to some other topics for the last 2 lectures. Another thing that was found a bit later by Parcole and George was that there is in fact a solution even at non-zero temperature. And this solution is for temperature and 1 over tau, much smaller than U. And this also is for this behavior is for omega much smaller than U. So in that regime, there's a solution here. It has the form of a conformal correlator of conformal field theories. You've seen those things. But at this point, what I told you last time was you could just take the solution and insert it into these equations and check that it actually works. And again, the notes have those calculations explicitly carried out. And you can also introduce the particle hole asymmetry by this exponential factor here. This turns out to be the way it appears at finite temperature. And you can kind of see why, it's easy to see, in fact, why this E here is the same as this E here. Because remember, so if I have this is the tau axis, you're going from 0 to 1 over temperature. And then this is an anti-periodic function. So if you're down here, g of tau, let's say it's doing that, how it's diverging here is diverging as 1 over square root of tau, and tau is going to 0. So whatever the prefactor here is 1. On the other hand, this is for 0 less than tau is less than 1 over t. It also has a divergence at 1 over t because sine diverges there. And this is related to, by anti-periodicity, to what happens here. So this is just related to that. And when you put time tau equals 1 over t, that cancels this t, and you get e to the minus 2 pi e. So the ratio of this to this is e to the 2 pi e. That's exactly what's over here. So this is the way it appears as a function of tau at finite temperature. And once you know it's an exponential, then the prefactor is completely fixed and has to be what's written there. All right, so that's a summary of how, as far as we got in understanding some of the properties of this model. Any questions?
Subir, so this is not understandable using sort of the Fermi liquid picture, right? I mean, you have this Q, which is the density. And
yeah, this is not a Fermi liquid at all. It's a non-Fermi liquid. It has no quasi-particle excitations. I anticipated that in the previous lecture where I showed you these very large number of low energy many body states.
Yes.
And what I'm going to do now is basically point the way anyway. First, I'm going to derive in a few minutes the fact that there's entropy is extensive as the temperature goes to 0. And that's by itself is an indication that this is not a Fermi liquid.
But what happens in the low Q limit? In the sense, is there a simple
0 what limit?
Q, the particle number?
As Q goes to 0? Well, then it basically the C minus becomes very small and C plus becomes very big because there's hardly any particles around. I mean, there are some issues of the solution even existing at very small Q. So for the most part, let's imagine that Q is 1/2 or close to 1/2, just to be safe.
I see. Okay. Thank you.
When Q is 1/2, then E is 0. Okay, because then it becomes particle hole symmetric, and that's in fact the structure of the Majorana version of this model. Any other questions? Yeah, please.
I have a general question, if I may.
Yeah, so this is a zero.
Yeah, I'll come to you next, but we have a question here. Yeah.
I think this model is a zero-dimensional model like this.
Yes.
So if I put it in a lattice, then the answer is known that it is still a non-Fermi liquid, or is it no Fermi surface?
It depends on how you put it on the lattice, and that will be the topic of the next 2 lectures. But this model, if you take a whole collection of this with hopping between them, then you find that at very low frequencies, it becomes a Fermi liquid again. But at higher temperatures, it is a non-Fermi liquid.
Okay.
To finding lattice models that are non-Fermi liquids down to 0 temperature, that's really the subject of the next 2 lectures.
Okay.
And we'll look at somewhat different models, which will and some of what we learn here will be able to apply there, but it won't directly be these models. In fact, they'll be much more realistic for the real systems.
Okay. So in that case, then the ratio C plus C minus will be 1 for a small omega. Yeah, I think
no. So what happens is that if you have a Fermi liquid, then this divergence gets cut off.
Oh.
Basically, it just becomes it's got some higher frequency part that's asymmetric, but then it just becomes like this. So yeah, C plus and C minus are defined then at higher frequency, and they could be away from one, but there's no divergence with the Fermi liquid. Yeah, so it's this diverging particle-hole asymmetry that's really the defining feature of this model, and it leads to all the strange properties. Yeah. Yes, Nadi, you had a question online?
Yeah, this is a question that actually you always ask me, which is to what extent is this model robust? Namely, if I deform it, the Hamiltonian a little bit,
Yeah.
how much of this story will change?
Well, so people have looked at, depends on how you deform it. So what will change the whole story is if you add a two-particle hopping. If you add a term like this, Tij, C dagger I, Cj, then it leads to this yellow line here. It cuts it off at some low frequency. And in fact, the scale it cuts it off is T squared over U. So that's definitely a relevant perturbation. If you add 6-body, 8-body terms, then they don't matter, and the solution is exactly that I've shown you. If you take what's called a sparse SYK, that's something I guess Brian Swingle and others have been studying, where you don't take, some of these you just set to 0, and the others are random numbers. It seems like you can go quite a distance and set many of them to 0, and you still get the same behavior. I think that's, yeah, those are some of the perturbations people have looked at. But yeah, so the short answer is there's basically one relevant perturbation, which is this hopping. So if you're going to realize this model in an experiment, then that's really the big thing you have to work towards, to get rid of this hopping.
How do you count the number, given that there are many TIJs, how do you count the number of operators? Is it 1 or is it n squared?
Well, yeah, so we're imagining that we're looking at the average theory where it just becomes a model without any spatial structure. And so then you're looking at, it's just 1 in that sense, yeah. So this Tij is somewhat related to, I believe, in the dual gravitational picture, some kind of wormhole that can open up a gap. Yeah, okay, so it's quite a strong perturbation on the holographic description.
But I thought that in that dual picture, this is the same as C goes to minus infinity to the gravity. And then there's an infinite number of relevant operators.
Oh, those are irrelevant. You're talking about those scaling, the higher dimension operators, the size, which have some irrational scaling dimension. There's an infinite tower of them, that's correct. But those are all irrelevant.
I see.
They have high scaling dimensions, so they won't perturb the low energy solution if you added them to the action, to the free energy. There is the leading irrelevant operator is the graviton mode. And that actually, when you go beyond the large N limit, does lead to some singular correction at low energies. So that's what I would call a dangerously irrelevant operator. That's the graviton, and everything else is just irrelevant.
Thank you.
Okay. All right. So now let me ask another question, which is something we often ask in Fermi liquid theory. When you're first learning about the specific heat of a Fermi gas, you do the Sommerfeld expansion at fixed chemical potential. And then you find that, well, actually, you're really working at fixed Q. So you have to make the chemical potential a function of temperature. Yes.
Do we know how much of this physics survives without disorder?
For what model? I mean, this, yeah, so this is the model. I don't know what you mean by without disorder. If you take this, I don't know. I mean, I don't think we really know. If you take them all equal, then yeah, then you don't get this physics. So you'll get some gapped state like a superconductor or something. But question is, what do you mean by without disorder? You have n to the fourth matrix elements. They have some values. Now you can put some patterns in them. Then if you have some special patterns, you probably won't get this solution. You may probably get some gap state of some type, depending on the kind of pattern you put into it. But what I would say is that if you just pick these numbers with probability 1, just for a single set of numbers, you will have this physics. There's a set of measure 0 where you get other things. Yeah, okay. So yeah, provided n is large, of course. So now the question, if you want to apply this to an atom, atom has 10 orbitals or 5 orbitals with some set of numbers like this. Will this be a useful solution? I don't know. Yeah, but when n is large, this is pretty generic. But there's no spatial structure here. I think the question of is there disorder or not becomes a question of if you have a spatial structure, then if your couplings vary as a function of space or not. That's really what we typically mean by disorder. There is no spatial structure here, so that's not a very relevant question. But it'll be a relevant question for what I'll talk about the next 2 lectures. Yeah, all of these questions will be addressed. We'll get much more. We'll talk about models with the spatial structure, which have breakdown of quasi-particles. And in detail, their properties are quite different from this, but many of the tricks we learn here are very useful there.
One more quick
Yeah,
question.
sure.
So when you added Tij there,
Yeah,
and you said that the behavior near omega equal to 0 changes.
yeah.
So I mean that the Tij you're also assuming to be disordered, or is it irrespective of that?
Yeah, I'm taking that be random numbers, but I kind of doubt it matters. Yeah, yeah. All right, so the question I'm going to address, which will seem like, some detail, but it's really the simplest way to understand what's going on here to the free energy and the entropy, which is what is the T dependence, T tends to 0 dependence at low of mu at fixed Q. And this is also a question that's very much related to particle hole asymmetry and C plus and C minus. So in a Fermi liquid, then what the Sommerfeld expansion shows us that mu is mu of 0 at 0 temperature minus some number times T squared over some underlying energy scale. T squared over EF. So this is one of the things you compute in undergraduate solid state physics when you ask what is the temperature of mu at fixed Q. So the kind of thing you do is you put Q is equal to some dE, some density of states times the Fermi function, e to the minus mu over T plus 1. And so all you're asking is if you keep Q fixed and you change temperature, what do you have to do to mu to keep the value of this integral the same? The rho of E is some smooth function near E equals 0. So that's what happens. So rho of E is just some smooth function like the yellow line, and you just have to figure out what should be the T dependence of mu so that this integral is T independent. And this function here, the Fermi function, has this feature that that's the step function at 0 temperature, but at finite temperature, it has this kind of form. And this area here, you can easily check in the Fermi function, is equal to this area over there. So if you just took the Fermi function by itself, then it actually preserves the integral under it because this area is equal to that area. That's just a property of this function, easy to check. This is mu over here, and this is E. This is the function I'm plotting. So this means if rho was a constant, then there's nothing to do. Mu is just a constant. Okay, so any mu t dependence of mu comes from the fact that rho is not a constant. So this number here involves the derivative of the density of states at 0 energy. You have to take the linear term in the density of states, and then gives you t squared correction, and it's t squared and not t because of this feature that these two areas are the same. Okay, so the correction is smaller than you would naively think because the Fermi function has this particle-hole symmetry. Okay, so now similar, I want to ask the same question here. Okay, so what I'm going to argue, so in the SYK model, mu of t is in fact a linear function of temperature, and the linear coefficient here is again this famous 2 pi e t. Okay, so there's some very careful arguments in the notes of various degree of rigor. I'm just going to give you a qualitative argument which gets the answer and gives you some idea what the physics of this is. But this is so, and this particular relation then will have very strong consequences. So the particle-hole symmetry, as already evident when we look at it, is extremely strong because it's a divergent density of states at 0 energy, and this means that the chemical potential of mu has to be rather strong to compensate for that. It's much stronger than in a Fermi liquid, and of course there are high order terms here, some powers higher than t. I believe the next term is t to the 3/2 or something like that. So these are complicated powers here, but this is the first term as universe. All right, so where does this come from? So what I'm going to do is first take this Green's function and evaluate a ratio of this Green's function at those two limits. So limit as temperature goes to 0 of g of tau over okay, g and tau is some small over g of 1 over t minus tau, where tau is of course much bigger than 1 over u, but it's much smaller than the 1 over temperature. Okay, so what happens when you take tau to be so small? Well, at one end, at tau equal to 0, as tau goes to 0, you just get the first term disappears, and you just get some whatever the constant is up front. So when you do it over here, what you find is that when tau equals 1 over temperature, then this thing survives, and so this thing is equal to, as you can easily check, is equal to e to the 2 pi e. All right, so we have this strange feature that this Green's function has this rather remarkable ratio, and we now want to ask, what does this mean for the chemical potential? Now, the trouble is, of course, in our solution, the chemical potential doesn't appear anywhere. But let's try to guess what the dependence, roughly speaking, at least to leading order at very low frequencies, much smaller than u, what the chemical potential dependence of the various terms might be. So let's take our look at, imagine u is essentially gone to infinity, and all of the electrons are basically at 0 energy. So we're going to just consider the Green's function of an electron, which is just where all the electrons exactly at 0 energy. So we take put all electrons at 0 energy. At E equals 0 in a chemical potential, and you change the chemical potential a little bit. delta mu. Then your Green's function, which you can just compute for a zero energy electron, is minus. I should have this. I don't have it memorized. It's important to get all the signs right. Okay, so the G0, this is the zero for zero energy electron, is minus e to the delta mu times tau over 1 plus e to the delta mu over temperature. So this is something that's easy to compute just from the definition of the Green's function. And therefore, now if I take this ratio, you'll find that's equal to e to the minus delta mu times 1 over t. The only thing that matters is this thing, minus 2 tau. All right. So what you see here is you get this tau independent term, which can appear in this ratio for a small change in the chemical potential. So now I just compare this change here to this here, and just map them, and I get exactly this relationship. So delta mu goes as proportional to temperature. And so this will be some constant, which is, must be exactly 2 pi e. And this term will vanish as temperature goes to 0 because this is proportional to temperature. So that's just a very qualitative argument. You can jazz it up a little bit, but it's simply the argument here is that we're looking at very, very low energies compared to U. U is gone to infinity, so may as well put everything at 0 energy to see the leading effect of a change in chemical potential, and you get exactly the effect needed if mu is a strong function of temperature. Okay. Furthermore, if delta mu over t is a constant as t goes to 0, then the density, which is e to the minus delta mu over t plus 1, is also a constant. So there's no variation in the density if you take delta mu proportional to temperature for essentially 0 energy electrons. Yeah, so this therefore answers what we were trying to answer. What is the chemical potential as a function of temperature, provided you keep the charge fixed. Okay, so now that we have this identity, seems like a boring identity, it has some rather remarkable consequences. Okay, I still want to keep that. So what we have established is a thermodynamic relation between chemical potential and temperature at fixed q. So in thermodynamics, the way you say this is d mu dt at fixed q is equal to minus 2 pi e. Okay, you might wonder why this 2 pi is floating around. It's everywhere. There's nothing, no rhyme or reason for it from this point of view. It's only when you go to either finite temperature correlations or you go to the holographic dual, and then E without the 2 pi is relevant, is the appropriate quantity. Anyway, all right, but what is this equal to? Well, there's something called a Maxwell relation. Which is that the rate of change of the charge at fixed temperature is equal to, well, there might be a minus sign somewhere. Yeah, minus d mu dt at fixed q. All right. So you've probably heard of Maxwell's relations in thermodynamics and promptly forgotten them. Nobody remembers them, but there's an easy way to recall them. This just comes from the fact that there's some free energy. There exists a free energy, F, which is a function of temperature in Q. And the chemical potential is clearly minus dF dQ at fixed T. And therefore, d mu dt, so that implies d mu dt is d by dt of d by df dq. So it's d squared f dt dq. But you also know that the entropy is minus df dt at fixed temperature. Therefore, df dt, sorry, I had the wrong way. df dt at fixed q, that's the entropy. And therefore, ds dq is again the same thing. It's df d squared f by dq dt. Okay, now if you have a function that's single valued, the order in which you take partial derivatives doesn't matter. So this must equal this, and therefore this must equal that. So the way I've defined things, the entropy is proportional to n, whereas the q is intensive. Q is not the total charge, there's a 1 over n in q. So to make this really consistent with my notation, you put a 1 over n here. I didn't put this in here to carry it through if you wish. Okay. All right, so what we have concluded is something quite remarkable, that ds dq as t goes to 0, so as t goes to 0, ds dq at fixed t is 2 pi e with a 1 over n if you wish, and this is not equal to 0. So what's this telling us? That at 0 temperature, well, so suppose q is 0. When q is 0, there's no particles around, surely the entropy is 0. But the moment you turn on now a non-zero q, E becomes non-zero, and therefore, the entropy S of q is n times an integral from 0 to whatever charge you're interested in of dq times 2 pi E, which is a function of q that you know from the Ledinger relation. So there's no way around it. There's an extensive 0 temperature entropy. And this is very closely connected to this very strong particle-hole asymmetry. Okay, so that's in fact roughly the way Georges Parcolet and I discovered this remarkable feature. Although at the time we discovered it, we said, well, this is terrible. We don't know of any systems like this. Something is wrong with this model or whatever. Also, it was in a different form of the model. It's not so easy to put in the computer and check it. But now, of course, we're very relieved that now after Kitay formed this model, which has all the same properties, you can now put it on a computer and compute the entropy. And those kind of computations from exact diagonalizing that Hamiltonian agree perfectly with this result. So we got it completely right. No factors of 2 or minus signs. Amazingly, that's probably due to Olivier Parcolet, who was very careful in computing these things out. All right, so that's the purpose of dwelling so much on the particle-hole asymmetry partly is to illustrate why this implies why this Maxwell relation a very large entropy, a very large density of states at low energy, just like I showed you in that numerical simulation. Okay, questions? All right, so as I said, there's a lot to cover in the properties of this model. I want to pick and choose. So what I think I'll do is I'll say a little bit about where that cinch came from, the theory of fluctuations about the saddle point, the structure of it, and this idea of the time reparamerization symmetry. And then if there's time remaining, I want to talk about a different model, which is actually the original model that Jinwoo and I studied, which is a spin model, which is much closer to at least the kind of physical systems we had in mind, like the disordered high temperature superconductors, and say a little bit about to the extent to which that applies to to the model with SU2 spin symmetry. Okay, so those are the two things I want to cover in the next less than an hour. Okay. All right, so let's talk about the theory of fluctuations. Yeah, we can do it up there. All right, so this is all was done, kind of in an ad hoc way, where we just did perturbation theory in U, and you average graph by graph. So that all looks good, but it doesn't give you any systematic understanding of where this is coming from and what the corrections would be, and so on. So in fact, in our work, we had a way of formulating this using a path integral. But now there's been much cleaner ways to do it using something called the G sigma theory, which is a lot easier to work with than what we had. But so that's kind of what I want to introduce, because it also highlights the important role of time reparamizations. Okay, so let's imagine what we want to do is compute, trace e to the minus beta h, the partition function. So that's of course impossible since we can't diagonalize this. But suppose we are going to look at the average of the partition function over all the properties. Now, in many cases where this is already a very dangerous thing to do. You don't want to average the partition function. You want to average the free energy, because that's what is the derivative of the free energy that gives you observable quantities. So that's often done by what's called the replica method, where you introduce an index n and you send it to 0. Again, I don't have time to explain that, so I won't go into it. But let me just say the SYK model, is such a self-averaging model. This sort of fluctuations are so weak that in this case, it doesn't matter. You just simply take the average and just work with the average partition function. Often that's not the right thing to do, but in this case, it turns out to be okay. And then you can check numerically that, yeah, it works perfectly. And there's some understanding of why that's the case, which was already in our very first paper. That's because this kind of model can't have a spin glass state. And the reason it can't have a spin glass state is because fermions never condense. Okay, but I don't have time to explain those rather cryptic words. Anyway, so for this system, because of the impossibility of spin glass order in the large n limit, you can just go ahead and average the partition function. Okay, so I write down the partition function. I'll be very schematic. Exponential minus c dagger d by d tau c. That's just the bare term. There's a mu term, I won't bother. And then you have a term like this, c dagger I, c dagger j, ck, cl, times ui jkl. Okay, and there's also a time here, d tau. That's kind of important. Okay. All right, so now the ui jkl are, and there's a n to the 3/2. Okay, so these are random numbers, so let's just average them. So, it's very easy to average. Let's assume they're Gaussian. And it's very easy to average the exponential of a Gaussian variable. You just take this, you take e to the minus 1/2 times its variance. So when you take the average, then what do you get? So you get z bar. Okay, it'll be exponential dot dot dot. These terms won't do anything, so I'm interested in this. And now I'm going to rewrite it in so you'll get sum on IJKL, only one sum on IJKL, because there's one sum here. And the different sites are uncorrelated, so they just add up. But you'll have two time integrals. That's really important. D tau prime. And then you'll get this whole object squared at two different times. So I'm just going to assert that I can rewrite that as sum on I, C dagger I of tau, C of tau prime, whole to the power 4. Probably a modulus. Why is that? Well, you just expand this out. The first term you put an I, the second term you put a J, the third term you put a K, and the fourth term you put an L, and expand it out. It's basically the square of this. Okay, so that's really why it's nice to have these independent random numbers. The sum over I all comes inside, and there's some factors of n I'm not keeping track of. So now in fact all of the dependence of I is here, and there's of course trace over I over here. So now what you can do is you can just do the sum over I. Even though we started a system with n sites, you end up with a path integral. This path integral has n things you're integrating over. Okay, n is huge. That's bad. But once it goes inside here, you can play a few tricks and reduce it to a path integral of 2 or 3 variables, not n of them. And that's an exact representation. So the way this is done is you do a Hubbard-Stratonovich transformation, which you've done many times in this course. The only trouble here is it's power 4, so you have to do the Hubbard-Stratonovich transformation twice, which is what I did in the first paper. But there's a quicker way to do it by introducing these G sigma way of doing it. So what you do is you introduce another variable, a collective variable, G of tau prime, which you define to be 1 over n sum on I, Ci of tau, C dagger I of tau prime, maybe with a minus sign. So this is the usual definition of a Green's function, except when you usually do it, you take an expectation value. Notice there's no expectation value. So I'm just calling this quantity here to just equal to this. And I'm doing a path integral over the C's. And I'm going to impose this equality by a delta function. So I'm going to write this thing as an integral. Well, I have the integral over Ci. Then I'll have an integral over sigma of tau and tau prime. And then I'll have an integral over G of tau and tau prime. So I introduce 2 new variables. These are like Hubbard-Stratonovich fields. I have 2 of them because there's a power 4 there in some sense. But it's just a quick way. You could have any power. You could still work with just 2. Okay, now I'm running out of space. So let me move that up. So it's that times exponential of what? You got sum on I, C dagger I, d Ci d tau. Then I'm going to impose this identity with a delta function. So I have sigma of tau prime times G of tau prime plus 1 over n Ci of tau Ci dagger of tau prime. And of course, integral over tau and tau prime. Okay, and then I have that whole term there. But now, oh, sorry, there's too many summations. The sum on IJKL shouldn't be there. All the sums are inside. So that thing is just G. So basically, I can write the last term as d tau prime of G of tau prime to the power 4. Right? So what happens here is, suppose I do this, the simplest thing to do is do the sigma integral. If I do the sigma integral, I get a delta function of this. Okay, then I can do the G integral and get rid of the delta function. And while I do the G integral, it equates G to this. So that comes back here. So I'm back to the original theory. Yeah, okay, all the factors of n are sloppy. They all disappear. In the end, when you do it properly, there's no 1 over n in the right places. Yeah, I haven't kept track of them. Okay. So therefore, this is just, dressed up Hubbard-Stratonovich transformation. Take the partition function, you average it, you introduce these two auxiliary variables, collective variables sigma and G, and you get an action schematically like this. Okay. Now, the important thing is you now look at the I dependence of it. There's the different I's don't couple to each other. There's an Ci here and a Ci here, and one side doesn't couple to the other side. So I can do the path integral for each side. It's the same path integral on every side. So I get the same path integral with the power n. And now that's wonderful because then there's an n in front of everything. So when the dust settles, again being very sloppy with all the signs and everything else, exponential, but roughly there'll be an n. Then you'll get the fermion path integral, which will be something like trace log of d by d tau minus sigma. And now you can see why we're calling it sigma, because it is the self-energy of the fermions. And then I have sigma g, sigma dot g, and I have g to the 4th. Okay, so that's it. So this is an exact representation of the average of the partition function, where I have reduced it from a path integral over n fields C to a path integral of 2 fields. Well, it's a bit more than 2 fields because these fields depend on 2 different times. They're full arbitrary function of 2 times. Sigma of tau prime and G of tau prime. So it's more than just 2, but anyway. These are 2 bilocal fields. So there's some kind of non-locality here, which the disorder average seems to be introducing. But when you look at any physical correlation function, there's nothing non-local, everything is local. But seems like, that you've got 2 different times. It's sort of like, there's a string that's connecting them, that's sigma and G. So it has some flavor of something which has an extended object, but it's still a local theory. All right, so now this theory, there's an n out front for everything. You can just look at the saddle point of it. If you look at the saddle point and you did all right, which is hopefully done in the notes, you get exactly those equations. Okay, so at the saddle point of this action is exactly those equations that we deduced earlier on just by doing an average perturbation theory. All right, so once you have the saddle point, then you can start to think about fluctuations. So I'm not going to go to that in any detail at all. There's a lot of very brilliant work done by Kitaev, Maldacena, and Stanford, and many other people who have understood quite a bit about how to do, at least pick out the most singular part of this path integral. And amazingly, that singular part of the path integral turns out to coincide with the path integral of some theories of 2-dimensional gravity. Explicitly, they're essentially the same. This is, however, a much richer theory. As written, it's not just gravity; it has many other things, because it's really an exact representation of the SYK model. All right. So, but what's the gravity part? Well, the gravity part has to do with the fact that this action has a symmetry, emergent symmetry at low energy. And that's really the main thing I want to mention before I finish this discussion on the SYK model. So, questions? I've been very schematic because, I mean, the steps are really quite simple. You can just see them. I don't have all the factors of 2 right, of course, but that's what the notes are for, where those things hopefully have been debugged. I've not been writing in the right place. Okay. All right. So what I want to do is at least show you a little bit about this emergent symmetry that's present in the action that's partly obscured now. But that's fine because I'm going to show you the symmetry not in the action, which is it's present in the action, but it's a little bit easier to see it in the saddle point equations. Okay. So one lesson we learned when we were doing this, the reason for going through this, is that the dynamical objects of the theory is not G of tau, you know, it's not, it's really G of 2 different times. So you know, so what we had, these theories are expressed in terms of G of tau prime, tau minus tau prime. That's the difference of 2 times from the definition earlier. But what we're going to do is actually think of it more generally as a larger theory where the degree of freedom is a bilocal field, which it's not required, at least in the path integral, to be a function of time differences. The average value, the expectation value of the Green's function or any physical object will only be a function of time differences. But when you're doing the path integral, you have to integrate over full independent dependence on tau and tau prime. And we are interested in that full path integral because we're interested in fluctuation correction. So when you're doing fluctuations, you really need to allow the 2 times to be independent. And this 2 times came, of course, from the disorder average, the fact that the disorder was independent of time. So let's just rewrite these equations in kind of a 2-time form. So, well, this is very easy. So the second equation, I'm just going to write sigma of tau prime is minus u squared g squared of tau prime g of tau prime tau. So if you took the saddle point, the action, which is a function of bilocal fields, and just look at the saddle point equation, this is one of the equations you'll get. Then you will say, well, since I'm the saddle point, I don't want to make time translational symmetry, but I will only look at solutions which are functions of 2 independent time differences. But since we want to understand not just the saddle point, but its fluctuation, let's look at it a little more generally. And what does this equation look like? Well, let's, yeah, sorry.
The point that you made that these observables would depend upon only the time differences,
Yeah.
but the path integral depends upon these bilocals.
Yes.
Does that mean that this is a redundant description?
No, no, it doesn't.
It doesn't.
It's just that the saddle point has time translational symmetry, but when you're doing the path integral, you have to really allow for all kinds of fluctuations. I mean, once you do the full path integral, any observable, any average value will have only dependence on tau minus tau prime. Right. You know, I mean, it's sort of similar to we have a classical path with a particle moving in a circle. The classical path is nice and symmetric, but the quantum mechanics ask you to sum over all possible paths, not just the circle. But any expectation value will have the circular symmetry. That's all there is to it. Yeah. Yeah.
Sigma and G, are they really 2 independent path integral variables? Because I have equations here with sigma and G.
So this is a saddle point equation. So in the path integral, they are independent. So not only are they're functions of two different times, they're also independent variables. Now, once you have this action, they're totally independent variables. I took that action and I looked at the saddle point equation. So these equations that I get, let's call that action S. So I evaluate del S del G equals 0, del S del sigma equals 0. And when I evaluate that, I get these two equations. Okay, but in the path integral, they're independent.
I started with only one path integral variable, that was C something.
The C is gone. And
Yeah.
C, I do the integral. That's led to the trace log.
Yeah.
The trace log came from the, and I had n different C's, so the trace log had a factor of n out front. Okay. Okay, so what does this look like in time space? Well, this looks like, let's see, some operator acting on, yeah, okay, d tau, yeah, d tau prime. I hope I get this right. It's d by d tau, tau, yeah, plus mu times delta of, well, you put it on the other side. Okay, this, again, you have to, I'm just rewriting this times this in some sensible form. Let me put it on this side. Delta of tau, tau minus tau prime of d by d tau prime plus mu acting on, and then I have minus sigma of tau prime, which acts on g of tau prime tau double prime, and that's equal to delta of tau minus tau double prime. Okay. So if you just rewrite this in double time notation, this is kind of what it looks like. This is a little easier to understand. You go, sigma goes from sigma multiplies omega, and anything that's a product in Fourier space is a convolution in time space. So you go from tau to tau prime and tau prime to tau double prime. The right-hand side is 1. 1 is a delta function from tau to tau prime. After you do the, if you take the Fourier transform of this equation, you'll just get exactly that for the case of functions that depend on time differences. If you take the saddle point equation, this is the kind of thing. All right. Now, the key observation is when we looked at the low energy solution to solve these equations, we got, G's, the saddle point solution was G of tau minus tau prime, went as 1 over square root of tau minus tau prime. And when we put in that type of solution, what would we find? We found that mu was equal to sigma of 0. So mu just kind of disappeared from the problem. And then the sigma of omega was square root of omega. And that was much larger than this. So we actually never made use of this. We just threw both of these terms out when we found the solution that I was describing in the beginning of this lecture. So what this means is that you can do a similar thing here. So in the low energy limit, just throw this term out. It's not important. So we're just looking at the low energy solution. And now the equations are very simple. Here's one equation. Okay. And the other equation is this following equation. D tau prime, sigma of tau prime, G of tau prime, tau double prime is equal to minus delta of tau minus tau double prime. So in the low energy limit, in terms of these bilocal variables, which are the right degrees of freedom for the fluctuations, the equation is just reduced to these two equations. Okay. And these equations, this is, let me call this equation 1 and 2. 1 and 2, these simplified equations are invariant under time reparameterization. Okay, sorry. Yeah, so that's easy to check once you know how to set it up. And so let me set it up. And where's the board thing gone? There. So these are very simple equations. They have no derivatives. And that's one of the reasons they're so rich in the structure and so have such a large symmetry. There's only a prefactor u over here. Other than that, they just involve, products of functions or the very trivial convolutions of functions. So you can, in fact, introduce another time. Yes.
I have one clarification before you erase this. How did the delta function work out in this path integral? You didn't put I in the usual way the delta function thing is put in.
For the sigma, you mean?
Yes.
Yeah, you can put it if you want, or you can just say that you absorbed it in the definition of sigma. So when you're doing the path integral over sigma, you have to be careful to, when you're doing the fluctuations in the path integral, that you go in the right direction so that the the delta function makes sense. So, this type of thing you almost often do. So, many times you have some integral over some lambda is e to the I lambda times some function of x, sorry. Yeah, so lambda times something, some other degrees of freedom. And you're doing this path integral of lambda. So here's the complex lambda plane. And often, typically what you find when you do this for a constraint variable, you have some fermions, and you say f dagger f minus 1 or something like this. What you find, so you have to do the integral along the real axis in this case. This is the lambda integral. But you find at the saddle point, actually I lambda becomes real because this is like a chemical potential for something else. And so the actual integral that you do is you find a saddle point somewhere here, and then you have to do an integral like this. Okay. So at the saddle point, the I kind of disappears. This is the lambda complex plane. The I kind of disappears, and this becomes a real number. But when you do the fluctuation, you have to remember the I and do the integral in this direction rather than that direction. Okay, then the whole thing is well defined if you do the integral in this direction. And there's a similar thing here. Here I've just absorbed, I've called this particular combination, if you wish, sigma. I didn't put the I. And at the saddle point level, it doesn't make any difference because sigma is the quantity that appears in the action is what I want to work with. But when I'm doing fluctuation corrections, I do have to remember, which I won't, I do have to remember that the fluctuation in sigma are along the imaginary axis, not the real axis. Okay?
Yeah, thank you.
Yeah. All right, so now we're going to talk about the time reparamerization symmetry. Of those equations right there. And so what is the symmetry? Well, you reparametrize time. So you have some clock that's running, and you have a new clock, which times runs monotonically though, but at a different rate. That's what time reparamerization is. And what do you do? Okay. So you have one time tau, and you introduce another time that I'll call sigma. And I'm going to make the following changes. So I'll call tau is f of sigma. So I have two clocks. There's the tau clock and the sigma clock. F is a monotonic function. You don't allow time to run backwards. Just goes from 0 to 1 over temperature. And so this is one clock, and that's another clock. Now you have this two-time Green's function, g of tau 1, tau 2. I'm going to write it as a function of sigma 1 and sigma 2, because I can always convert from tau to sigma by solving this equation. This has a unique solution. The inverse is unique. So assume I know that solution. So this I'll call f prime of sigma 1, f prime of sigma 2, times minus 1/4 of some g tilde of sigma 1, sigma 2. You can view this as a definition of G tilde. I just define G tilde to be this. Satisfy this equation where f is any function you like. You pick a monotonic function which has an inverse, and then you define a new function G tilde, which is just if you know G of tau 1, tau 2, you can figure out what's G sigma 1, sigma 2. And similarly with sigma, I do the same thing. I'm going to have here f prime of sigma 1, f prime of sigma 2, minus 3/4 here, times sigma tilde of sigma 1, sigma 2. So basically, I'm just doing a change of variables. I change from variables, I have those two equations, 1 and 2. The variables are capital sigma, capital G, and tau prime. And now I have a new set of variables, which is G tilde, sigma tilde, and little sigma 1 and little sigma 2. So that's the new frame, and I have a new frame with the sigma clock. And in the sigma clock, I define my Green's function to be the tilde Green's functions. What are the equations obeyed by the tilde Green's functions? Well, they're exactly the same. Just replace G by G tilde and tau by sigma. And you can check that. So now we can show, put it over here. So these change of variable implies, it's easy to check the first one, that sigma tilde of sigma 1, sigma 2 will be u squared times G tilde of, okay, well, now I have tau 1, tau 2. All right, forgive me. Sigma 1, sigma 2 squared and G tilde of sigma 2, sigma 1. So the problem has the same form and different, no matter how you set the clock. And that's the time reparamerization invariance. So this is quite easy to check. Well, you can go the other way, I suppose. So if I insert G and sigma in there, on the left-hand side, well, that's, yeah, so this is the third power of this. So everything it's trivially true. I mean, it's easy to see, it's obviously true. A little more tricky is this one. There you have to use the transformation of the delta function, and that's where these will come out to be more useful. Right now, the fact that this is the three times the power of that is simply because there's 3 times the power here back to here. Okay, so for the other one, you have to do a little change of variables, and then you see that it actually works out. So there, what do? You say d tau prime. Well, you're changing from tau, well, let's call it tau, yeah, let's call it tau prime to sigma prime. So that'll become d sigma prime times d tau prime over d sigma. But what is d tau prime over d sigma prime? That's f prime of sigma prime. Okay, and so on. So now you have sigma times G. So sigma times G will give you G tilde with appropriate arguments times sigma tilde. But now you have to look at the powers of these guys. And so what will you get? Sigma times G will give you, well, whatever. I don't think I can do this on the board. I hope sigma will give you this, and that will give you this, but there's all different arguments here. So you have to be very careful with the whole thing. So you'll get some various, okay, let me at least try. So you have to be careful. Sigma tilde of sigma prime. And then I have to plug this in here. I'll have f prime of sigma, f prime of sigma prime to the minus 3/4. And then I'll get G tilde of sigma prime, sigma double prime, and I'll get f prime of sigma prime, f prime of sigma double prime to the power what? Minus a quarter. And the right-hand side will be delta minus delta of sigma minus sigma double prime. And that will be divided by the transformation of the delta function of f prime of sigma. All right. So now this tells you the sigma equals sigma double prime. So this sigma equals that. And therefore, so since these two are equal, then this will become f prime of sigma to power minus 1, which will cancel this. Okay, so that's progress. So this will cancel with this, which will cancel with this. And then this will give you f prime of sigma to the minus 1, which will cancel with this. So you're done. I even got it right. Okay, so they all cancel out, all the f's cancel out from the change of variables of the integrand and the change of variables of the delta function. All right, so that's the starting point of a huge amount of development. The observation of this time reparamerization symmetry, it connects naturally then to various theories of gravity. And it's these all of these functional integrals that you perform then to some approximation, and that in the end, the state of the art is that this result that I showed you, that the density of states is n times S naught. S naught we showed you how to get from the chemical potential argument, and all of this song and dance gives you this cinch function here. So this cinch comes from the leading, by integrating over the soft mode associated with this time reparamerization. So another important point is that this time reparamerization is not an exact symmetry. This term here that I threw out is not invariant under time reparamerization. And so in fact, you have to do the integral very carefully, but you just pick out the effects of this very weak term. And when you do that carefully, this is how you get the cinch factor. So that's quite an amazing calculation. I didn't have anything to do with it, but some of it is reviewed in the notes. And there's also a review article that is cited on the website that written with Debanjan Chowdhury, Antoine George, and Olivier Parcolet. That's officially the notes for this section of the course. And there, there's a fairly complete derivation of where this comes from. Okay. Questions? All right, so then I have 15 minutes. What I want to say is a little bit about a more physical model, at least from our point of view, or somebody studying cuprates or correlated electron systems, rather than this SYK model. I mean, the beauty of the SYK model is that it's solvable. You can also study it numerically. You can do fluctuation corrections. You can do so much that you can't do with the model I'm going to now present. And it's directly connected to black hole physics, but its connection to condensed matter system is a bit more tenuous. People are trying to quantum simulate it, but let's see if they get to it. Okay. So let me, I can keep that. All right. So let me just say a few words about the connection to more physical models for condensed matter anyway. So the model that we were interested in, and many others in those days and since, is the following model. So we take a bunch of sites, I less than j, going from 1 through n, with some exchange couplings jij of spins. Take Si dot into Sj. So this we're going to take to be S equals 1/2 spins. And the model I'm going to say a bit about is the model where this Gij are random variables. Okay, so S equals 1/2 spins of SU2. Now, of course, this model is been a huge focus of this course. We put it on a square lattice, we put it on triangular lattices with translational symmetry, and we found spin liquid states, we found magnetically ordered states, we found valence bond solid states. That's all we've been talking about for a month or two. So now we just take the same model and put it on and frustrate the hell out of it and just take random numbers that couple any pair of spins. Okay, this is the model we love to solve. This is not solvable. The only thing you can do is put it on a computer. And that's, we've been doing a lot of that in the last couple of years in work jointly with Antoine George's group. And so I think we are understanding pretty well now what some of the properties of this model are. And the main result is that there is, if you look at its ground state, it's nothing like the SYK model. It looks like, in fact, has a spin glass ground state. But if you look at quite a wide range of intermediate frequencies, it shows clear signals of spin liquid behavior. So you can think of the SYK in this context as some kind of spin liquid with non-Fermi liquid spin-ons. And there's a lot of evidence that this model actually has those, but not all the way down to zero energy. At some low energy scale, the spin glass takes over. Okay, so what is the spin glass, in case you haven't heard about it? So a much simpler model would be the model that Parisi solved, sometimes called the SK model. This is the Sherrington-Kirkpatrick model. So this is a purely classical model where your Hamiltonian is again the same kind of thing. I less than j equal 1 through n of jij, random numbers, with just sigma I, sigma j are classical bits. Sigma I equals plus minus 1. So this is the model that was solved by Parisi, for which he got the Nobel Prize. And it has also a lot of very rich physics. It's connected to neural networks, and there are connections to all kinds of things in machine learning and various combinatoric problems. So here you're just trying to find the thermal states and also the ground state of just assign these bits so that this thing has the smallest possible value. That turns out to be an extremely hard problem. What Parisi showed was that there was some very sophisticated way of understanding some statistical properties of the solution, of the thermal properties of such a model. Okay, which I certainly cannot cover in the next 10 minutes. But what's the basic property of this model if I'm looking at the ground state? Well, these are classical variables, and they're going to the ground state. Well, the spins are going to freeze in some configuration. Now, if I had an ordered magnet, they will spin, if all spins up or all spins down. So that will be a ferromagnetic state. Or you can get an anti-ferromagnetic state. So here, you would get some expectation value as t goes to 0. If you pick a fixed set of jij and you cool the system down, it will freeze into some configuration where the sigma I will be not equal to 0, but it'll be all random functions of I. It will depend on which side you look at. Some will be up, others will be down, and so on, depending on what. No, this is no lattice. It's everything connected to everything else. Fully connected cluster. Just like, I from 1 through n. I mean, the SYK model is even more dense. Everything connected to everything in pairs of 4. This is in pairs of 2. Okay. So this is sometimes called the fully connected cluster. So very far from the square lattice. All right, so this is a random function of I. But so if you just average this over configuration, you still get 0. So how do you distinguish between different ground states of a model like this? Well, you introduce what's called the Edwards-Anderson order parameter, QEA. And that's you look at the thermal expectation value of some sigma I, and you square it, and then you take the average. So at high temperatures, this will all, each term, sigma I will be just 0 because the spins are equally likely to be up and down, just like in any other system. There's still a Z2 symmetry here, but at low temperatures, the Z2 symmetry is broken in some random frustrated way, and which is different for different GIJ. So this is where the configuration of GIJ really matter. And so you have to worry about replicas and replica symmetry breaking just to properly capture the very chaotic dependence of the sigma I on the GIJ. It's hard to predict what it is. In fact, there's infinite number of solutions. That's what replica symmetry breaking tells us. The system has many different valleys it can freeze into. But in each one of those valleys, as long as it freezes in, you take the square, then this particular object will be the same in every valley. And that's the Edwards-Anderson order parameter. Okay, so that's the spin glass state. So that's a classical problem. It has to freeze into a spin glass state because there are no fluctuations at 0 temperature. But now you make it a quantum problem. So now the question is, what about this problem? Do the spins freeze as you lower the temperature? Or do they fluctuate? Is this expectation value of S in a spin liquid, this particular expectation value would be 0 on every side if the spins are fluctuating a lot, as it is, the chiral spin liquid or the Z2 spin liquid. So here's a very frustrated system of quantum spins. Maybe this freezing doesn't happen. All right, so the answer we know today from numerical studies, it does happen, but very weakly. This QEA is extremely small. And at higher frequencies, it looks like the SYK model. So why does it look like the SYK model? Or how do you get a spin liquid solution of this model in a controlled way? And that was the question we answered. We said, well, and it's the same method that we've been using all through the course when we did the Kondo lattice and spin liquids. You go from SU2 spin symmetry, you go to SUM. So I can look at exactly this model, but for SUM, not SU2. And the basic result is if you take this model, let me just call it HSUM. So if you take, first of all, you take the limit of n going to infinity. So you have infinite number of sites with some spin. We are interested in the m equals 2 case of that object. Is there a spin liquid? Is there a spin glass? What is the spectrum? This is what we're interested in. Can't solve it. So we take another limit. Afterwards, m goes to infinity. And this is solvable. And what you find is that the spin-ons, so if you write your spin variables S alpha beta in terms of spin-ons, like we've been doing all along, F dagger alpha F beta on every site, the F spin-ons form SYK state. Well, of course, we didn't call it that, but that's what they do. So it's again, a theme that we discussed a while back. You take some spin model and you write it in terms of partons, and then partons can do funny things. Partons can have Chern numbers. Parton can, pair, form superfluids, and that has interesting consequences for the spin correlations. And here, what the partons are doing are forming an SYK state. And so that leads to a very interesting spin liquid with lots of properties that you can compute and compare with numerics. And let me just say that what you find, and this is very rough, that for frequencies, so this particular model, or this model for finite m, there's a frequency scale. Let me call it omega star, which goes as e to the minus square root of pi m. For omega much than omega star, this model looks like a spin glass, not too different from the Parisi solution. And omega bigger than omega star, there's a J here, but still smaller than J, of course. It looks like a SYK spin liquid. So this you can show analytically for M large. And so now the only question is, as M goes to 2, is omega star small enough, much smaller than J? And so this you can only address by doing numerics, and it looks like, all right, I'm out of time, but we have several papers on this topic, which are cited in the review article. Actually work done by my student, Henry Shackleton, especially. And there's really, I would say, rather good evidence that M is small enough for even at M equals 2. E to the minus square of 2 pi is about 0.08. So that's good. Gives you a very wide regime where you see spin liquid behavior. And this kind of, from the cuprate point of view, I think is very much the kind of situation I talked about last week about the cuprate phase diagram. There seems to be a wide intermediate regime where you see spin liquid physics with the pseudo gap. And then at low temperatures, some ordered state takes over. This is one model where you can actually work out a lot of these details. How you go from a kind of an ordered confining state as far as the spin-ons are concerned to a deconfined spin liquid of these gapless spin-ons. So at least for the random model and M large, we can really work this crossover from confinement to from spin liquid to ordering in some detail. So there's a few recent papers on that, one by my student Maine Christos and Felix Hale. Okay, so stop there. Any questions? And then we'll start something. We'll talk about systems in finite dimensions, non-Fermi liquids in finite dimensions next time. And please let me know if the people at IAS, if you rather start a bit earlier. It's no problem as far as India is concerned. So, any questions? Okay, thank you. See you on Wednesday.